Welcome, everybody. I wanted to give a further introduction to clustering and in particular K-means clustering. So when you look at this data set in 2D, how many clusters or groups do you see? Frankly, there's no right answer. Maybe you see 2 clusters, or maybe you have better eyesight than I do, and maybe you see 3 clusters, right? Or maybe you even see different clusters than those 3 I've circled. So there's no right answer, but there's a whole zoo of algorithms that try to take a data set and group it up into parts where data points in the same part have more in common than data sets in 2 different data points in 2 different clusters. So maybe you see 2 clusters, but your friend sees 3. You're both right. I want to talk about K-means clustering. This is a common clustering algorithm. It's very fast to implement. I think it's a fun algorithm to try to implement. The one downside, which is a big downside, is you need to decide how many clusters you want in advance. So K is going to be the number of clusters you'll produce, and you need to decide K in advance. People have studied how do you find K. So maybe you try different values of K, and then there are ways to evaluate which value of K, which number of clusters do you think is the best or correct. But those are all pretty ad hoc. So there's no right answer to how many clusters you have in most data sets. Just like in this data set, there's no right answer as to whether it's 3 or 2 clusters. Okay. So I'm going to explain K-means clustering with K equals 2. So we're going to find 2 clusters in this data set. And here's how you do it. First, you just choose 2 potentially random points as your initial centers. Okay. So this point in yellow and blue, they're not even points in my data set. My data set is all the points in black. But these are just my 2 guesses at, initial centers for where my clusters might be. Once you have 2 initial centers, you associate each data point to the closest center. Okay, so each data point in black, I've looked at the distances. Is it closest to the blue center or the yellow center? And I've drawn a dotted line to denote that. At that point, the data points inherit the color of their center. Okay, so all the data points closest to the blue center become blue. All the data points closest to the yellow center become yellow. And now we forget about the centers. Okay, and these are our first clusters. Okay, we did okay, but not great. These are our first clusters in yellow and blue. But let's do better. The next centers that we use are the averages of the blue points and the averages of the yellow points. So we take the average of the blue points and we get this X as this center point. And we take the average of the yellow points and we get this X, this center. Once you have those centers produced as the average of the blue or the average of the yellow points, you forget the colors of your data points. Your data points, again, are just unaffiliated data points. And now you compute distances between each data point and the centers, and you associate each data point to the closest center. And again, colors get inherited. So these blue and yellow colors get inherited to the data points. And now we'll forget the locations of the centers, but maintain the colors. We'll do this one more time, and you'll see now that we'll keep these good clusters forevermore. So we compute the average of the blue and the average of the yellow data points to get our new centers. We associate, we forget the colors on the data points. We associate each data point to the closest center. And then we give data points the color of their center. And then we're left with our clustering. So you'll notice that, my centers here weren't great, right? This yellow center was a little further away. I would have wished it were sort of here, right? But I got good colors, right? And then I went through the center process again. My centers were much better. And once I got back to here, the colors on the data points were the same as the step before. So there's no need to keep going through this. We're going to keep these two clusters forevermore. How much did this depend on the initial random location of the centers? It definitely depends. Okay, so for some data sets, if you start with your centers one way, you might get different final clusterings than if you start with your centers in a different position. But for pretty run-of-the-mill data sets like this one, this algorithm is quite robust to different choices of initial centers. So let's change my centers. Okay, let's start with these two centers, right? You might think, aha, I'm going to break this algorithm where, I don't know, maybe I'll get like yellow data points and blue data points. But no, this is still going to work pretty well. Okay, so we have our initial centers in blue and yellow. We compute distances and associate each data point to its closest center. And then we use those connections, data points to the closest center, to assign the colors of the centers to the data points. Forget about those centers and compute new centers. Let's take the average of the blue points as the new blue center and the average of the yellow data points as the new yellow center. All right. Now, forget the colors of the data points. Associate each data point to its closest center. Okay. The data points inherit the colors of the centers. We discard these centers. We compute new centers. The new blue center is the average of the blue points, etc. And now we associate each data point to its closest center. You're going to see that this blue data point is going to swap, right? It's going to swap centers. So associate each data point to its closest center. Here we go. And then data points inherit the colors from the centers, discard the centers. And then from here, you can see that the colors are going to remain fixed. Find the new centers. Now the centers are very good in the middle of the clusters. Drop the colors, associate data points to the closest center, inherit colors, remove the centers, and will remain here evermore. Okay, so that was my introduction to K-means clustering. A disadvantage is you need to choose the number of clusters in advance. An advantage is it's very fast to compute. And for run-of-the-mill data sets, things depend on the initial choice of centers, but not in a bad way, not overly so. What public questions do you have?
So I'd assume there'd be some sort of like stop function or something that would run once a cluster didn't take over a point from another cluster.
Yeah, I would say that's right. Although I would say the stop function here is not just based on a single cluster, but on all the clusters. So this algorithm is fast enough that you can just run it until none of the clusters change, and then you're done.
Okay, yeah.
Yeah. Great question.
Related to that, do you ever have to worry in this about cycling, where you could have something where there's a small perturbation or just like flip like one or two data points back and forth between clusters?
Great question. I love it. Okay. So, Lander's thinking of this algorithm in steps, which is a good way to think about it. Think of the steps as, initial assignment of blue and yellow to the data points, and then the next assignment, and then the next assignment, and then the next assignment. And then eventually I'm claiming that you get to this fixed assignment where you just stay at all these points are blue and all these points are yellow forevermore, okay? So you're in this periodic orbit of period 1, right? You keep returning to the same point after each step. Lander's asking, is it ever possible to end in a periodic orbit of period 2 or 3 or 4? So maybe there's like 2, 3, or 4 approximately equally good ways to cluster these points. Can you end in the cycling pattern where you keep rotating between different clustering patterns? I do not know the answer to that, Lander. I would love to know the answer to that. My hope is that it is possible to get the cycling pattern because I'd love to see that example. I wouldn't be surprised, however, if the result is that you always end at this fixed point